So in this video we're going to simply look at one integral, the integral from 2 to 10 of the function 2x squared dx. And we all know how to solve that with the traditional technique, and our actual value, or exact value, which I'll call x for error analysis, is 661.3 repeating. So using the midpoint rule, we know with the midpoint rule that's basically a Riemann sum with the midpoint, and we're going to look at n equals 1, 2, and 4, and then I give you the answer for 8. So let's go through. The first step in the process is computing delta x. Delta x is b minus a over n, and in this case delta x is 8 when we have just one rectangle that we're working with. So the area of that rectangle is simply delta x times f of 6, which is the midpoint of that rectangle. So m1 is equal to 576. If we're going to use two rectangles to approximate the area under the curve, then you're going to compute a delta x, which is 4, and you start at, again, you always start at a, which is 2, add delta x to it, continue to add delta x to it until you reach b, which is 10. So you have two rectangles, and the midpoint of each of those is just found by, the endpoints of the rectangle divided by 2. So the midpoint here, m1 is 4 and m2 is 8. And compute the area of both of these rectangles. Here's rectangle 1, rectangle 2, using the midpoint rule. And you get an approximation for m of 2 to be 640. And you can see we're starting to narrow in on that exact value. It's still not great, but we're doing okay. So n equals 4. I didn't go into as much detail with the calculations. Hopefully you get the idea by now. But again, you compute delta x, and delta x is 2. You set up your rectangles, find the midpoints, and then substitute that midpoint into the function to get the height of the rectangle and multiply by the width, which is delta x. And then you add them all up for m of 4 equaling 656. And then I just give you m of 8. It's getting tedious, which is why we're going to be doing the lab, to do all the manual computations by hand here. So let's look at the next approximation technique, which is the trapezoid rule. So with the trapezoid rule, we know the formula is here. And again, you start off by always computing your delta x. For n equals 2 trapezoids, we're going to compute where you start. You start at A and you end at B, and then you just add delta x to A and you start off that way. So 2 plus 4 is 6, and then 6 plus 4, so plus 4 is 10, plus 4 is 6. So now just using the formula, 1/2 f of x0, which is f of 2, plus f of x1, which is f of 6, and then plus 1/2 x of 2, and that quantity added together and multiplied by delta x. So that comes down to evaluate it here, and t of 2, the trapezoid rule, is 704. If you want to use 4 trapezoids, same process. Compute your delta x, find all your x sub zeros, right? X of 1, 2, 3, and 4 in this case, because you've got 4 subintervals, and then plug into your trapezoid rule, and you get t of 4 equaling 672. And then n of 8, you go through the same process, delta x, right? You get the idea, hopefully. And t of 8 is equal to 264. One thing that we know from the prior video is that we can use a shortcut if we have the midpoint calculated for this integral, which we do. So t of 2 times n, and n is equal to 4 in this case. We're looking for, We're looking for the approximation t of 8. and 8 is just 2 times 4, then using that formula you take the average of t of 4 and the midpoint of 4, and you do get indeed the same answer, 664. So that's the trapezoid rule, and the last one is Simpson's rule. And with Simpson's rule, you get a much better approximation, a little bit more complexity to the formula, but certainly worth it in the end, because you can see that with n equaling 4, we hone in very quickly to the exact value. Alright, so here's your Simpson's rule formula. Okay. And then you just find your delta x, which is 2 when n equals 4, and then you've got your x sub k values, and substitute into the formula f of x sub 0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 plus your last is just f of x4. So again, you have the alternating of these 4 2's going on, okay, till you exhaust the number of subintervals, and then you multiply that quantity by delta x over 3, which is simply 2/3. And when you do that, algebraic work, or mathematical work really, numeric, is 661.33 with 3 repeating. So you get right there with n equals 4 using Simpson's rule. And then here's the shortcut for Simpson's. S of 4 is the same thing as 2 times n, and n is equal to 2. And that is the shortcut. You take 4 times 2 times n, or 2 times n of using the trapezoid. It's relying on the trapezoid. Minus t of n divided by 3. So here's your formula, and you end up with the same value. So here you can see the 3 different numerical methods done by hand for the simple integral of 2x squared from a lower limit of 2 and an upper limit of 10 over the interval. So hopefully that will give you a good conceptual understanding of what's going on with Maple, what Maple is doing for you.